So today we're going to be talking about hash tables. More specifically, we're going to talk more about the kind of usage of hash tables rather than the kind of underlying mechanics of how they work. So the first thing to notice, think about what a hash table is just think about it as like another container as an alternative to your vectors, decks, or linked lists that you never use. It's data structure to store data. So to motivate why we have hash tables, let's think about some of the weaknesses of your other containers. There are two that, for me, that really stand out. The first is that for other containers, there's only one way in which you can reference your data items, and that's with ordered integers. For example, vectors, you label your data 0 through n-1 for n sets of data. Same with deck. For linked lists, you actually don't have this referencing at all most of the time. Another weakness for these types of data structures is and so in that case, sometimes you would want to, going back on that, sometimes you would want to actually reference them with some other things. For example, let's say that you want to reference people by their social security numbers. Social security numbers, although you are ints, they are usually not ordered from 0 to the number of people in the United States, for example. They are usually much larger and spaced out numbers. Or maybe you would want to reference movies by their genre, and movie genres are usually strings. Another weakness of these alternative types of containers is that, as mentioned previously, there are probably in previous lectures, they are very inefficient in terms of inserting and deleting from the middle of them. These are usually O of n operation. This usually takes O of n time, which for vectors and decks, which obviously you would hope you could do something better than this. Hence why we have hash tables, which, as you may guess, their strengths lie in almost exactly the weaknesses of the other containers. With hash tables, you can reference items in your hash tables with essentially almost anything that can be integers, large integers, sparse integers, doubles, strings, chars, even your own created objects as well. Usually they are very efficient in terms of inserting and deleting from any location of the hash table. They will be usually average case O of 1. Sometimes this does generate to O of n depending on implementation, but again, we're not going to go into that for now. However, all of this efficiency in terms of time does come at a cost, and one of the biggest costs is memory. For your other data structures, your memory is usually very close minus the overhead of making your data structures. For example, if you have O of n for your vectors, if you have O of n items, for the most part, your memory overhead to support it is approximately O of n, plus or minus, kind of like some of the additional O of 1 vectors and stuff. For hash tables, however, the memory needed to make effective hash tables, depending on the implementation, can be several times that of the number of items you actually need to be stored, which costs money and money for like companies and whatever to implement. Another reason that hash tables may be a weakness is that the items that are in it are kind of like all over, inserted and stored all over the place. For example, for vectors and decks, there's very strong locality of reference in that items that you insert next to each other are stored next to each other. As a result, things that are related are close to each other. For hash tables, that's not the case. Storing items that might be kind of like heuristically close to each other can be stored completely random locations and are nowhere near each other. Another weakness with this is that hash tables aren't really that sortable. So if you ever want to do a sort operation, hash tables are usually not the way to go. Lastly, for hash tables to be effective, you usually want a good hash function. Luckily, the standard library and most implementations have a good one provided for you. So we can, in C++, a hash table is implemented through something called an unordered map with a key value pair. you insert these key value pairs into your hash table, where the key is the index. Again, that might be kind of your social security number or like the genre of your movie or whatnot, and then the value is like the thing, like the value that you're actually storing. Some common operations that you'll use is the .find and .insert. And they're both kind of like pretty self-explanatory in what they do. .insert puts in new key value pairs into your hash table, and .find retrieves them and like either retrieves them if they exist or tells you that they do not exist in your table yet. And generally, for your projects, you want to use these operations as opposed to the bracket operator .at, because they have more consistent and better controllable behavior. And lastly, here's just some code ripped from a CPP reference for your reference on how this stuff can work. That's it.